All right, so for some reason, the audio is not encoding on the video that I made in class. So I'm just going to kind of going over the notes. So if you need to watch it again, hopefully this will help. So this is a lesson where we're recovering area arc length, slope, and speed of polar coordinates. So if we go back to rectangular coordinates, we started off by approximating the area under a curve using rectangles. And the area of one rectangle is the width times the height. And in this case, the width of the rectangle was our delta x sub I, and the height of the rectangle was f of x sub I. And then that's just one of the rectangles. But if we put an infinite number of them to get the actual area and add them all up, that turns into a definite integral. So our f of x sub I turns into f of x, our delta x sub I turns into dx, and voila, we have the actual area under the curve. So we do something similar with polar coordinates, but rather than looking at area under the curve in polar coordinates, we actually look at area inside the curve, radiating from the origin and between two rays. So if we take a look at this blob, and let's say I want to find the area in between these two rays, so it was this area here shaded in yellow, we can, instead of breaking the area up into rectangles like we do for rectangular coordinates, we're going to break the area up into sectors. And a sector is just a pie slice or a fraction of the area of a circle. So what fraction is it? Well, we have this angle in here. So if we want to look at the area, for instance, of this sector, you have this area here, or sorry, this angle here, which is the change in our deltas. The change in our thetas. So it's our delta theta sub I. And that's the part of the whole entire circle. So this represents the fraction of the circle, and then pi r squared is the area of the circle. And then we can just cross out the pi's and we get the formula. I'm just going to write it as 1/2 r squared delta theta I. And then again, that's just one sector. So to find the area of all of the sectors, we turn it into a definite integral. So we have 1/2 r squared and then d theta. So this can be our formula, and that gave us this. Here we are now in a much more formal form. So if f of theta is continuous function, then the area bounded by the curve in polar form r equals f of theta, and the rays theta equals alpha and theta equals beta, with alpha less than beta, very important. The area is equal to, and you can write it either way. They're basically the same, except this says r squared, and remember r is f of theta, so we could just say f of theta squared as well. So now we're just going to do that. Now remember, the work comes in trying to find alpha and beta, trying to find those limits. So then we were messing around in class. I just kind of gave this example. Let's say that these rays, and you could look at these rays as as pi over 4 or any coterminal angle to that. And if I wanted to find the area of the shaded region, we have to be careful what our limits of integration are going to be. So it may be tempting to go from pi over 4 to 3 pi over 4. Because this is at pi over 4, this is at 3 pi over 4. But we can't do that, because if we went from pi over 4 to 3 pi over 4, that would actually get the white region, the unshaded part. That's not what we're looking for. So then it might be tempting to reverse them. Okay, well, we want to go from 3 pi over 4 to pi over 4, so let's just reverse the limits. But again, you can't do that because of this part right here. Your lower limit has to be less than the upper limit, and 3 pi over 4 is not less than pi over 4. So one possible answer is this: starting at 3 pi over 4 and increasing until you get to 9 pi over 4. So starting at theta equals 3 pi over 4, we increase, we go in the positive direction, and the next angle we hit here is going to be 9 pi over 4. So that's one possibility. And then somebody in class asked, well, could we do this? And this actually works as well. Negative 5 pi over 4 would actually put you right here. So that started in a negative direction, but then we increase until we get to pi over 4, and it still works. It's still getting this yellow region. So just kind of some examples, thinking about the limits to start with. So then we looked at this example. Find the area of the inner loop of the limacon r equals 2 cosine theta. And we didn't have the graph. I challenged them. Let's try to find the graph first. So one way that can help you find the graph of a polar curve is to look at the corresponding rectangular curve. So look at it in rectangular coordinates. So we just graphed this. It's a cosine curve, amplitude of 2, shifted down 1 unit. And so that's what we have right here. And some points that can be useful to help you translate this into polar are anytime you got mins and maxes, anytime you got intercepts, and remember our trig functions will have this midline. So any points that hit the midline, they line up with our quadrantal angles, so they're useful. So all these points can be useful. So we labeled them all. We ended up not using them all, but we just kind of, had in our mind what they were. And we went ahead and also found the value of the X-intercepts. So B, F, H, and L. This helped us find it. We set the equation equal to 0, solved, and we got these. So like this is pi over 3. This is 5 pi over 3. And then we have the coterminal angles to those. So how does this help us get this? Well, we started off with G. Personally, I like to start with, I just look at the positive, a positive period. And so starting at theta equals 0, this is at r equals 1. So starting at theta equals 0, that's this ray right here, we went out to r equals 1 and plotted the point. There's point G. And then point H, well, let's see here. That's at pi over 3 with a radius of 0. Remember, once you have a radius of 0, you're automatically at the origin. But what's happening between G and H? So the angle is increasing, but the radius is decreasing. So we're increasing on the angles, we're decreasing on the radius. So to go from point G to H, we're going to imagine going around, increasing in angles, but as we increase, we're going to get closer to the origin, and that's how we know we have this kind of curve to the polar curve. And then we did it again, now from H to I. Well, I was at pi over 2, but the radius is negative 1. So here's pi over 2, but the radius being negative 1 means we go in the opposite direction, 1 unit. So we had a point right there. And then what's happening between H and I? Well, between H and I, again, the radius is the angle is increasing. So think about it this way. We're pi over 3 to pi over 2. So it would be in quadrant 1, but then the radius is all negative. So that puts us into quadrant 3. So we have this kind of curve. And I'll just do a couple more. From I to J, well, first of all, J is at pi with a radius of negative 3. So here's pi, but negative 3 means we go in the opposite direction, so that's where point J would go. Between I and J, the angles are pi over 2 to pi, so that would be in quadrant 2, but all the radii are negative, so that puts us in quadrant 4. So to go from here to here, I know I'm going to stay in quadrant 4. And then it just kind of keeps doing that, and we can see it does this curve. Now remember, there's really no starting point to this curve in rectangular coordinates. Who says we have to start at 0? We could start at -2 pi. I could start here. Like, who knows where the starting point is? But if we follow the flow of points, it's going to trace, as the angle increases, the path along the polar curve is doing this. Now we want to find the area of the inner loop. So the inner loop is going to start here, go around until we get to there. Radius of 0, increasing to radius of 1, decreasing back to radius of 0. Where do we see that happening here? We see it happening right here at this point. Radius of 0, increasing to radius of 1, decreasing back to radius of 0. So where were these angles? At -pi/3 to +pi/3. And that's how we knew our limits of integration. That's where most of the battle is in just setting up the equation, because then we have our formula. It's 1/2 times the integral of r squared d theta. And this was r, it's given right there. So now we know that's our integral for finding the area. And then we just started it. We didn't actually finish it. If you were going to evaluate this, you would want to square it first. You'd have to FOIL it all out. And then I just reminded them, how do you evaluate the integral of cosine squared? That's where the power reducing formulas come in. And you can memorize the power reducing formulas, or they just come from the double angle formula for cosine. So cosine 2 theta, since this is cosine squared, I used the version of cosine 2 theta that had cosine squared in it. And then actually hidden in here is a 2 cosine squared, and I have 2 cosine squared right there. So I just solved for that, and then I put it in here. And then we have the rest of it. And then it would become very straightforward to integrate. And then just as a reminder, if we had a sine squared in our integral, you could use this version for cosine 2 theta and solve for sine squared. And there's your power reducing formula for sine. So that was our first example. And this was the longest one. But then just a reminder, if you're going to do area between two curves, so just like between two curves with rectangular, we're going to subtract, but we no longer have a top minus bottom curve or a right minus left. You always want to think it outer curve minus the inner curve. Outer curve, inner curve. So for example, if I had this, and I just made up some blobs. Here's one blob. The pink curve is r equals f of theta. The green curve is r equals g of theta. Let's say I wanted to find these pink regions here. Well, the pink regions, this first region, the green is the outer curve and the pink is the inner curve. But then it swapped, pink being outer to green being inner. So you would actually have to make two different integrals. And you'd have to find that point of intersection to find your theta. So then your first integral goes from theta equals alpha to theta equals theta 1. And then it's 1/2 times the integral, outer curve squared minus inner curve squared. And then for this pink region, it's the same thing, but now our limits are going from theta 1 to beta. And now the outer curve is f and the inner curve is g. So outer curve squared minus inner curve squared. Don't forget those 1/2. That's just part of the formula. So there's area, and then we looked at slope. So slope is not bad because, I mean, it's just tedious, really. So we're talking the slope of the tangent line. So the slope of the tangent line is still going to be the change in the vertical with respect to the change in the horizontal distance. So still dy dx. But we're talking r and theta. Well, that's okay. We know dy dx can be written as dy d theta over dx d theta, and we know what x and y are in terms of r and theta. So we can just take the derivative of y, that'll be in the numerator, take the derivative of x and put it in the denominator. Just remember that these r's are not constant. They're also functions of theta, so we had to use product rule. And so you can take the video or pause the video if you need to and easily see that using product rule on y gives you this numerator, and product rule on x gives you this denominator. So some people choose to memorize this formula. Some people choose to just remember how to get it, whichever one you want. But that's finding slope. Then we looked at arc length. And arc length, polar equations can be thought a lot of like parametric, because we have an equation for x and we have an equation for y. And so remember, in parametric form, arc length was this. But we can just let x of t be x of theta and y of t be y of theta, and just plug it in there. And we could do that, but it turns out that this actually, when you use these functions for x and y, it actually simplifies down really nicely. And so that's what we did here. X prime of theta squared, if x is arc cosine theta, well, x prime is this, but then you got to square it. And then again, if y of theta equals this, y prime squared is this squared. And at first it looks pretty ugly, but you can see it condenses really nicely. We squared this, that's this whole line right here. And then we squared this, which gave us this whole line right here. Well, these two terms cancel out. From these two terms, if you factor out r squared, you get sine squared plus cosine squared, which is just 1. So it's r squared times 1. And then similar thing happens over here with these two terms. Factoring out the r prime squared, it's going to get multiplied by 1. So it turns out it simplifies to this, which is really nice. So it turns out for arc length, when r equals arc length of, that's supposed to be of, let's fix that. But arc length of r equals f of theta is just this. R squared is really f of theta squared. R prime squared is f prime of theta squared. And we get that. And then you can just use the formula. And then the final thing was speed. And then just remember speed, because speed's going to be the derivative of your arc length, just like it was with parametric. Your speed is just this. And then that was it. That was the end of our notes. There's nothing left. So hopefully this video will help, and I will see you guys in class. Bye.